Hello, everyone. This is actually an extension to the workshop that we had on 25th of June 2026 on statistics for engineering research. In that workshop, we covered several parts, several sections, but because we had to stop the workshop about 2 hours before the planned time, uh, I was not able to cover all the the material that I was expecting to cover. So therefore, that day we decided to have another workshop on a later date, but somehow it got delayed. So I thought that until that workshop is done, I'll prepare a video on the material that we were unable to discuss on that day, right? So mainly there was a request on a discussion uh, about regression analysis. So therefore, I thought I will prepare this video on correlation analysis, starting with correlation analysis and then going to regression analysis, right? So I hope this will help you uh, to understand certain concepts in both of those correlation and regression. And that might help you actually to discuss whatever the remaining concepts or whatever the parts that you didn't understand from the video when we meet next time on to complete the remaining part of the workshop, right? So this actually contains a certain large number of slides. You see that about 170 slides here. So it will take some time. So therefore, I will probably break this whole presentation into several parts, right? I cannot say exactly the length of each part because I will stop wherever I feel like stopping for part to part. But it will take about 2 to 3 hours, I guess. So therefore, let me do it by parts. Probably it will take about 3 parts, I guess. Right. So we'll start with the scatter plot and measures of linear association and nonlinear association, uh, nonlinear monotonic associations, and so on. So the whole video, several parts, will include that part, scatter plots and measures of linear association and nonlinear association, and then some description about how to test uh, hypothesis concerning the correlation. And then we'll come to regression. There, I will first discuss a little bit briefly uh, about the theory behind regression, and then we will look at some examples and so on. I remember you told me that you have already covered these topics in your lectures also. Therefore, probably these will not be that helpful. I don't know. Anyway, I thought maybe I should give you this presentation as a part of the workshop that was not completed, right? Okay. So let's start with the first item. Here, actually, we are going to look at mainly the correlation analysis. Right? So correlation analysis is used to study the strength and the direction of the association between two quantitative variables. Quantitative variables, right? Uh, In addition to the correlation analysis, there are some other analysis similar to that, some usually called test of association or association analysis. But here mainly because in the engineering fields, usually we have numerical data. I am considering here only the correlation between two variables, say X and Y, both are quantitative. Right? So I have seen that in many research papers, people directly uh, calculate something called the Pearson's correlation coefficient. And when we calculate the Pearson correlation coefficient using a computer package, usually uh, it gives you the correlation coefficient as well as some output related to a test of hypothesis. And researchers directly report those things without considering any other things, and then sometimes give wrong interpretations also. So therefore, I thought I should uh, explain certain important things related to this something called correlation analysis. Right. So before computing or testing any hypothesis regarding correlation, there is a very important step that you should follow. That is to explore the data using some graphical method. Right? So, what is the most suitable graphical method to explore the relationship between two variables? The scatter plot is the most suitable graphical technique to explore the relationship between two numerical variables. So therefore, a scatter plot is the first and essential step in correlation analysis. It shows the observed pairs of values, xi, yi. We have paired observations always. From each person, we may have two observations, x and y, and maybe from some concrete strength measurement experiment, you may have some, say, for example, the amount of some chemical or the amount of cement or something, and then y may be the strength, right? So like that, for a given value of x, you have a certain value of y, and that will be considered as a pair of observation. So each of these pair can be considered as a point in the two-dimensional plane. So when we plot these pairs as points in the two-dimensional plane, you get a graph. That's what you call the scatter plot. So scatter plot helps you to identify certain things, few different things. What are they? Well, first of all, we can see whether there is any evidence of a relationship. Right? Whether there is any evidence of a relationship. That means whether there is any kind of pattern. Right? So if there's a pattern that you can see somehow, then that is an indication that there may be a relationship, some kind of relationship between X and Y. And then if you find out that there is a relationship, or if you find out that there is some evidence of a relationship, then you can ask the question, is the relationship look like a linear relationship or a non-linear relationship? Right. In this case, the word linear, by linear, we usually mean a straight line relationship. Non-linear means some other relationship, not a straight line, right? So that is the meaning of the linear here in this situation when you're talking about correlation analysis. Remember, when you go to regression analysis, still we use the word linear. In that case, we say linear regression, for example. In that case, the word linear has a different meaning. It doesn't mean a straight line always. Right? So that is some important thing to understand. When you talk about correlation analysis, linear usually means a straight line relationship. In the regression analysis, it means something else, and I will explain that when I come to regression part. Right? So whether the relationship is monotone but not linear, right? There can be some non-linear relationships, but they can be monotone. Monotone means either increasing or decreasing monotonically, but may not be a straight line relationship. Also, whether there are some clusters or subgroups, whether there is an evidence of some clusters or subgroups, right? Whether there are extreme values or influential observations. So all these things can be explored using a scatter plot. So let us look at some examples of scatter plots. So here, if you plot your observations, pairs of observations X and Y's, you might see this kind of relationship when you plot the data. You may see that you can consider these data points as scattered around some straight line, right? This is one possible straight line that you can draw through the points. So this is the kind of relationship that you usually call the linear relationship. Right? The points are scattered around a straight line. So they are linear means a straight line. So points are not necessarily on the straight line, but they are scattered around a straight line. So in that case, we say there seems to be a positive linear relationship. Positive linear relationship if the slope is positive of the straight line that we can draw through the points. In this case, positive linear relationship. In addition to this, the sign positive and linear, and we can also say something about the strength of the relationship. For that, actually, the graph itself is not sufficient, because usually the same graph, if you draw using a different scale or in a larger graph, you might see that these points are scattered more scattered, right? If you draw the same picture in even a smaller area like this, all the points will be look like close to the line, right? So whether the points are close to the line or far away from the line cannot be directly observed using a graph. Therefore, it's better to use some numerical measure, right, to get some idea about the strength of the linear relationship, whether they are close to the line or whether they are far apart, right? So therefore, we will later talk about some measures of the strength of the relationship, especially when there is some evidence of a linear relationship, right? So this is one possible situation. Using the graph, we can say there is a positive linear relationship, right? There is some evidence of a positive linear relationship. But notice that here we have only several observations coming from some experiment or some observation and study. But if you do more experiments, you will get more observations, right? So therefore, this set of observations can be considered as a random sample coming from a larger set of points, which we call the population, that would be generated if we repeat the experiment, right? So this is only a random sample from that kind of a population, right? And here, this graph, you can see that points are uh, when the x is decreasing, y values tend to decrease in general. And you can also consider this as a straight line relationship approximately. One might even consider some as a non-linear relationship, but one might consider it as a linear relationship because there is some possibility to draw a straight line through the points. Of course, we can draw a curve also through the points. Later on, we will discuss which uh, model will be a suitable model. But anyway, for the moment, I am going to consider this as a uh, evidence of negative linear relationship. Negative because the slope of the straight line is negative. It's a linear relationship because the points can be considered as around this straight line here. If you consider this scatter plot, you can see directly, actually clearly, there are some points, but they are not actually around a straight line, right? Can clearly see that they are around some non-linear function. We don't know what the function is, but if you draw a line through these points, what will happen is actually for a certain part, all the points will be above the line. And for some other parts, all the points will be below the line. In that kind of situation, we don't call it a straight line relationship. What we need is whatever the scatter has to be randomly scattered around whatever the function that we are considering. Like for example, here we can consider this scatter as scattered around a straight line because here if you consider here in this region you have points above and below. In this region you have points above and below the straight line. In this region you have points above and below without any other particular pattern, right? So therefore it's reasonable to consider this line as going through the points. It's not like that. If you draw any straight line here, for example, right, then these points, all these points, right, for a certain region will be below the straight line, and all these points will be above the line, right? So therefore, it's not possible to consider it as a straight line relationship. So therefore, I'll call it monotone, positive, non-linear relationship. Monotone means they are increasing in general, the same direction. Monotone. Positive is going up, therefore positive. Non-linear relationship. If you consider this one, this can be considered as monotone, negative non-linear. Again, you cannot consider it as a straight line relationship. If you draw any straight line here, uh, for a certain part, all the observations will be above the line, and for a certain part, all the observations will be below the line, right? It's not randomly uh, scattered around whatever the line or the curve that you are considering for all x values. So therefore, in this case, it's better to call it a monotone, negative, non-linear relationship when you have this kind of situation. And this is also clearly not a linear, not a straight line relationship. You cannot draw a straight line through all the points here, definitely. But it is also not a monotone, non-linear function. It's not linear, though. It's non-linear. It's clearly non-linear function, but it is not monotone, right? In this part of x values, it's decreasing. For this part of x values, it is increasing. So therefore, we can just call it a non-monotone, non-linear relationship. It's not monotone. It's a non-monotone, non-linear relationship. Right. If you consider this one, this is completely different from the previous one. In the previous ones, there was some pattern that we saw. Right? Like here, the observations are increasing, y values are increasing with x on average, right? in general, right? Here y values are decreasing with increasing x in general. Here again, y values are increasing with x values increasing in general. Here y values are decreasing when x is increasing in general. But here, yeah, here for certain part it's decreasing, for the other part it's increasing. So there is again a pattern. There's a pattern. But here, there's no pattern like that. I mean, at least I cannot see any pattern here. Only thing you can see that these points are around some horizontal line, right? Some horizontal line. So therefore, in this kind of situations, we say there is no evidence of a relationship, right? There is no evidence of a linear relationship, or there is no evidence of a non-linear relationship, right? So now you can see that you will not be able to say any of these things if you didn't look at a scatter plot. If you just had some several XY values, right, you will not be able to say any of the things that I just mentioned about these relationships if you didn't have a scatter plot. Right? Okay, now, as I mentioned earlier, when there is a linear relationship like this or like this, you might be interested in mentioning the strength of the linear relationship, how strong the relationship is. Right? Like for example, if you look at these two graphs, you can definitely see from these two because scales are comparable. Here, it seems to be the strength of the linear relationship seems to be a little stronger, right, than here. Right? So, but if somebody else drew the same points in a larger graph, he might even say this is strength is less for this graph than this one. Right? So therefore, it's better to have some measure that everybody will get the same value for this graph, no matter what the scale of the graph is. And similarly, everybody will get the same value for this kind of relationship, no matter what the scale is. Right? So that is where the measures of strength is important. Right? Now, if there is evidence of a linear relationship, the commonly used measure of the strength and the direction, of course, comes with that, of the linear relationship is called the Pearson's correlation coefficient. Pearson's correlation coefficient. That is when uh, there seems to be a linear relationship between x and y. Right? So there's a formula here. I have just given you the formula, but usually you can get any this thing using a computer package, right? Pearson's correlation coefficient measure the strength and direction of a linear association or linear relationship between two quantitative variables. Right? So usually be denoted by simple R. Right? Simple R. These are xi, yi values, x bar, y bar, usual things that you know. But if the data are sometimes maybe even when the data are not numerical, but even the data, if the data are ordinal, there is another measure. But mainly when the relationship is not linear, but monotone. Right. Suppose when you draw the graph, you see that there is some relationship. Definitely there is a relationship, but it is not a linear relationship. It can be considered as a monotone relationship. Then again, in that case, what is the strength of that monotone relationship is a question, right? So in that kind of situation, people usually use a different measure. It's called Spearman's rank correlation coefficient or simply Spearman's correlation coefficient. Spearman's rank correlation coefficient measures the strength and direction of a monotonic association between two variables. So it is given by this formula. Here you can see now you don't see any xi, yi values, but you see some di, where di is the difference between the rank of the ith pair of observations. So that means what you do is you actually don't consider the actual values of x and actual values of y. What you do is you rank all the x values, taking x values as one set, and you rank all the set y values as another set. So now for each x1, y1, you have a rank 1, rank 2, right? Rank of x, rank of y. And for another pair, rank of that x and rank of that y, like that. So you have pairs of ranks now. So di is actually the difference between those two ranks for a pair, given pair. Di is the difference between the ranks. For example, rank of yi minus rank of xi. Right. Here, what we do is we consider the squared value. So therefore, it doesn't matter whether you consider rank of xi minus rank of yi or rank of yi minus rank of xi. Doesn't matter because you are squaring. So anyway, that is how it is calculated. So therefore, there are mainly two measures that people use. One, Pearson's correlation coefficient, usually denoted by R, is used to measure the strength of the linear relationship when there is evidence of a linear relationship. On the other hand, Spearman's correlation coefficient, here I have denoted by R subscript S, but in some other situations, it may be denoted by some other letter, because here in this presentation, I use R for the Pearson's correlation coefficient and RS for the Spearman's one. Now, one might ask, isn't a linear relationship also monotonic? And can't we use Spearman's correlation coefficient in that situation? Of course, you can, right? Every linear relationship is a monotonic relationship. But not every monotonic relationship is a linear relationship. You saw that using the examples. So therefore, when there is evidence of a linear relationship, the better measure is the Pearson's correlation coefficient. But when there is evidence of a non-linear but monotonic relationship, the better measure is the Spearman's correlation coefficient. Right. So when the relationship is linear, Pearson's correlation coefficient is generally more appropriate than Spearman's rank correlation coefficient, because Pearson's correlation coefficient specially measures the linear association. So as I mentioned again earlier, if you didn't look at the scatter plot, you don't know whether there is a relationship or not. First of all, if there is a relationship, what is it, whether it's a linear one or a non-linear one, you don't know any of these things. Therefore, you will not be able to even select a suitable measure in that case. Right. So that is one problem that I have seen in research papers. In most of the research papers, regardless of what kind of relationship there might be existing, people used to calculate Pearson's correlation coefficient and report it. So that may not be the most suitable correlation coefficient in that situation. So therefore, the recommendation is to explore the scatter plot first, and then based on that, decide which type of measures are suitable. So scatter plots should always be examined before calculating and interpreting a correlation coefficient. Now, what are the properties of these quantities R and RS? Yeah, when you calculate this quantity, whether it's R or RS, they are always between -1 and +1, right? where -1 and +1 are very, very rarely occurring, almost no situation, but theoretically they can be -1 or +1. Practically what you get is a negative or positive decimal number between -1 and +1. Right. So depending on the value that you get, people use different wordings to interpret the, the, the relationship that is appearing in the correlation coefficient, in the scatter plot. Right. So if the R value or RS value is close to +1, for example, 0.8, 0.9, that or any value close to that, it can be 0.85, 0.87. Then usually people say, in case of R, people interpret it as a strong positive linear relationship. In case of RS, if it is close to 1, then it may be interpreted as a strong monotone positive linear relationship. Not linear in that case, monotone. And similarly, if the values are close to -1, then you use the word negative instead of the positive in the previous interpretation. On the other hand, if those values are, say, close to 0, like 0.1, 0.2, even 0.25, people usually describe them as no relationship. No relationship, positive or negative, between 0.25 and -0.25 and 0.25. People interpret that as an indication of a no relationship. Right? If in case of R, it indicates there is no linear relationship. Right? In case of RS, it indicates there is no monotone relationship. Close to 0. That's what I mentioned, right? Between -0.25 and +0.25, roughly. This is not a universally accepted rule, but generally that is the indication. On the other hand, if uh, R is, say, in the positive side between 0.25 and 0.5, say, for example, that kind of values indicate weak linear or monotone, depending on which correlation coefficient you are using. But the word is weak linear relationship or a monotone relationship. If it is positive side, you can say weak linear, positive linear relationship, or weak monotone, positive relationship. If on the other hand, if it is in the negative side, then the word negative can be put with it. And if R is, say, between 0.5 and 0.75 or 0.8, usually it is considered as a moderate relationship. Again, depending on whether you are using R or RS, you can add the word linear or monotone. Right? So moderate, positive, linear, or moderate, positive, monotone relationship. Right? Similarly, in the negative side, in that case, the word negative should be there. So that is the general wording that people use. But remember, what important thing is, here you are interpreting a sample quantity, right? Sample correlation coefficient. It's not a population quantity, right? So that is one important thing to remember, right? So what you are interpreting is what you saw using the sample of observation. So sample correlation coefficient shows, for example, the relationship between X and Y in the sample is positive, strong, and linear. Right? It doesn't mean that in the population also the relationship between X and Y is the same. It doesn't necessarily mean that. So that is an important thing to understand. We will talk about a little later how to decide about the actual relationship in the population based on the sample correlation coefficient. That is something different. That is called what you call the inference, making inference about the population correlation coefficient based on the sample correlation. Right? Therefore, usually we carry out some hypothesis testing and so on. Based on that, we make some conclusion about the population correlation coefficient. So that is an important thing to understand. Many people seem not to understand that. Right? They don't understand. They just calculate the sample correlation coefficient and then think there is actually there will be and there is actually the same correlation in the population also. No, that may not be the case. Right. So now let us look at some examples with the correlation coefficients, right? So suppose you have this kind of scatter plot. When you plot your data, you get this kind of thing. So one thing you can, directly by looking at, you can say, okay, there seems to be a linear relationship and it seems to be a positive linear relationship. But what is the strength, right? So in this case, because it seems to be a linear relationship, it's better to look at Pearson's correlation coefficient. So I calculated the Pearson correlation coefficient. I got this number 0.89 something. It's enough to calculate up to two decimal places, but I have recorded here the whole answer I got using the computer. So it's close to 0.9. So usually in usual words, we would say there is an evidence of very strong, or you can say don't have to use the word very, but you can say there seems to be a strong positive linear relationship between X and Y points in the sample, in the sample, in the sample that we have got, right? And similarly, if you have this kind of situation, yeah, one might say, okay, there is a linear relationship because we can consider a line going through these points without any particular pattern, leaving any other pattern. Then any other pattern means most of the observations are above the line in a one part, and that kind of pattern will not arise if I draw a straight line through these points. Therefore, it's reasonable to assume the relationship is linear, but negative in this case. So what is the strength? Well, I calculated the correlation coefficient. You can see now I get the value negative something. So you can see that the correlation coefficient not only gives you the strength, it gives you the direction also. Right? If you get a negative value, it tells you that relationship is negative. So it's like 0.83. So according to the usual way of interpreting, this may also be considered as a strong, right? A negative linear relationship, strong, right? Usually people sometimes more than 0.75 is considered as an indication of a strong relationship. Some people may consider it to be, if it is more than 90, to be strong. That's different, subjective. As I mentioned, there's no universally accepted method, right? So if I use the rule, if it is more than 0.75 to be called strong, then it will be a strong negative linear relationship. And here you can see that if you look at the graph, of course, I don't see any pattern here. So therefore, I would just directly by looking at this thing, I will guess that there is no linear or non-linear relationship in this case. So, but anyway, I just calculated R here. And I can see that R is negative, but R negative doesn't mean here, there doesn't mean that there is a negative relationship or something. And we can look at that R is also very small, 0.1. Right? So whether it's positive or negative, because this kind of small correlation coefficient is usually interpreted as no relationship between X and Y. No relationship. There's no evidence of a relationship between X and Y in this case. Now, if you look at this one might consider it as a straight line, but I think the better to consider it as a non-linear but monotone, because you can see that the points are going around a curve, not around a straight line directly. Right? So I would guess that the relationship that is apparent in the sample is a non-linear relationship, monotone, non-linear. So therefore, in this situation, Pearson's correlation coefficient is not very suitable. It's better to look at Spearman's correlation coefficient. So, so we decide that the Spearman correlation coefficient is the good one, but just to show you, I have calculated both here, right? So RS is that's the Spearman's one is 0.93, and Pearson's correlation coefficient is also 0.93. Actually, Pearson's correlation coefficient is larger than the Spearman one here. But better to use Spearman correlation coefficient when you are interpreting. Right? In this case, no matter which one you use, your interpretation will be close. But if you use Pearson's correlation coefficient, this number you will be interpreting it as a strong positive linear relationship, which may not be the correct one. But if you use this one, you may be interpreting as a positive monotone relationship. Positive monotone relationship, strong positive monotone relationship. So that is the difference. Right. Okay. Now, if you look at this graph, there is definitely some non-linear relationship, non-linear pattern here, but it's not a monotone non-linear one. So therefore, RORS will not be suitable here. R is not suitable because it is not a linear relationship. R is not suitable because it's not a monotone non-linear relationship. Right. So in this kind of situations, calculating RORS and interpreting it would be not useful. Right. But if you somehow calculate it, for example, R is in this case negative 0.05. You don't have to even consider the sign here. It's very close to zero. So that indicates, of course, there is no linear relationship. There's no linear relationship. But it doesn't mean that there is no relationship. There is definitely a relationship. So one error that many people do is they look at this thing, right? It is close to zero. So they say there is no relationship between X and Y, which is completely wrong. R being close to zero in this case, if you want, you can interpret as there is no linear relationship. That is correct. But that is not enough expression, right? Enough interpretation, right? If you had looked at the graph, you could have clearly mentioned that there is a non-linear relationship. That would be more informative than saying there is no linear relationship. And similarly, this one with close to zero, it says there is no monotone non-linear relationship. Again, that is correct in that case, if you say that. But that's not enough, right? You can say better than that if you had looked at the graph. So that tells you how important to explore the scatter plot is. Right. Now, there are some other situations you have to be careful when you are interpreting RORS. This is a situation like that. Now, suppose your scatter plot is something like this. You can see that clearly there are two groups here where this group here, if you consider this group, the correlation between X and Y in this group may be weak or almost no relationship, something like, or maybe weak relationship. But for this, there is some kind of moderate or strong relationship just by looking at, and you can consider it as a positive relationship also, linear. So you can say all of those things by looking at for this part. But if you ignore the grouping or clustering, if you consider all these things together, And then in that case, it might look like again a linear relationship combined together. And one might even say it's a strong or moderate relationship. Right. So now let us look at the correlation coefficients individually for these two groups and collectively to get some idea. Right. So for cluster one, for this cluster, I calculated R in this case is just 0.18. So that indicates actually there for this cluster, there is almost no linear relationship, right? Very small. But for cluster two, it's 0.78 R. And therefore, there is maybe we may interpret the relationship here between X and Y as some kind of moderate positive linear relationship. On the other hand, if you put both together, it will tell you that it will be interpreted as a very strong positive linear relationship. And that interpretation is not going to be a good interpretation. It's not a good interpretation. Actually, what you have is there are two groups. Within the first group, there is almost no relationship, linear or otherwise, actually. In this case, there is a linear relationship, right? So therefore, if you didn't look at this graph, what you would do is you directly calculate this quantity and you would interpret it as having a very strong positive linear relationship, which is meaning less actually in this case. Wrong. So that is again shows you how important the scatter plot is. Right. In this case, it's important to us identify the clusters. The correlation analysis performed without considering the grouping structure may lead to misleading or erroneous conclusions. Right. So in order to see the clustering, you need to look at the scatter plot. And this graph also has the same idea, but now even a different situation. For one cluster, the relationship seems to be a negative relationship. For the other cluster, the relationship seems to be a positive linear one. In this case, maybe a negative linear relationship. Right? So if you don't look at the graph scatter plot, you will put all these data together and calculate the correlation coefficient. So you may get 0.92 in that case. And you will be interpreting it as a strong positive linear relationship, which is completely wrong. Right? But on the other hand, if you had the graph, you would definitely see these two clusters, and then you will definitely look at the correlations within each cluster, right? You will not even try to calculate the correlation by putting all these things together, right? So here in that case, clearly this will be in the first cluster, there is a strong negative linear relationship. In the second cluster, there is again a strong or moderate positive linear relationship, right? So that shows the clustering, right? And then scatter plot is useful in identifying clustering also. Another use of a scatter plot is to identify something called extreme values. Extreme values. And if you have a graph like this, you can see that this part of the graph as behaving according to some relationship. All those x values are in this region, all the y values are in this region. But there are some three observations. Sometimes you might have only this, or only this, or only this, maybe two of these like that. I'm showing all possibilities here. This observation, you can see that this x value is within the normal range of the other observations, but the y value is quite different from the normal range of y values for the most of the bulk of the observations. So therefore, this observation may be an extreme value, may be considered as an extreme value with respect to its y value. Right? This observation is maybe extreme with respect to its y value, but not with respect to the x value. On the other hand, this observation, y value is within this range of the bulk of the observations, but the x values for this observation is completely much larger than the range of the maximum of x values. It is not in this range, right? It is not in this range. So this may be an extreme value with respect to its x value, but may not be with respect to the y value. On the other hand, this observation may be an extreme value with respect to its x value as well as with respect to its y value. Now, these extreme values may occur due to different reasons. One main usually occurring reason is the errors, typing errors or recording errors, measurement errors, and that kind of things. So before you calculate the correlation coefficient to measure the strength of the relationship, whenever you see this kind of observations, whenever possible, if possible, go back and check whether this might be an error due to recording or some other measurement error. And similarly, whether these are some errors that you can maybe correct, right? If you don't find any reason, or if you find that it's actually an actual observation, don't remove that. Keep it. Right? Don't remove that. But if you keep it, then correlation will give you a wrong idea about the actual relationship for the other bulk of the data. Because this might be an influential observation, right? It may have a large influence on the correlation coefficient, right? So therefore, for example, if you consider the bulk of the data, there seems to be a strong positive linear relationship. But if you calculate the correlation coefficient for these observations, it might give you a smaller value indicating a kind of a moderate positive linear relationship. And similarly, if you calculate the correlation coefficient with these observations, the value that you get might be largely different from the correlation coefficient you get from these values. Right. So whenever possible, if you find it is an error, correct it. Or if you find it is actual value, keep it. But in that case, be careful when you are interpreting the correlation coefficient. You have to be careful when you are interpreting the correlation coefficient, right? If you calculate the correlation coefficient. Now, in this case, I didn't look at the correlation coefficient considering each observation separately. What I did was for example, assumed that these three are some wrong observations, and therefore I removed it and then calculated the correlation coefficient. In that case, I got 0.92. But on the other hand, if I calculate the correlation coefficient with these observations, I get only 0.66. So if somebody calculates the correlation coefficient directly without looking at the scatter diagram, he will get this answer. And he will interpret it as the relationship between x and y for the sample is some kind of moderate linear relationship. Yeah. That may not be the correct interpretation if, for example, if these observations were errors and they should have been removed or corrected. Right. On the other hand, if you are keeping these observations because they are actually correct, then when you are reporting this kind of correlation coefficient, you have to give a little bit more details and explain that there was some relationship for the bulk of the data, the correlation coefficient for this one, but here the correlation coefficient is smaller because of these extreme observations. Even though they are extreme, they are natural observations, they are correct observations. So like that, when you are interpreting it, you have to give a little bit more details and correctly interpret rather than just saying whether there's a moderate or linear without looking at the graph. Right. A non-zero, so that is the actually what you can do as a descriptive analysis of the correlation, right? As a descriptive correlation analysis, there what you do is only look at the sample of data that you have, and whatever the conclusion you are making based on that is only about your sample. So you say there is an evidence of a strong positive linear relationship in the XY values in my sample of data. That's all you can say, right? But sometimes that may not be enough. Most of the times, actually, you are really interested in the relationship between X and Y in the population. That population may be a really existing population or maybe a population that would be generated if you generate more XY pairs based on more experiments. And that would generate a population of XY points. And in that population also will the relationship be the same as in the sample that we have observed? That may be an interesting question to ask, right? Especially if you are looking at whether there is a relationship or not. What you are looking at is actually whether there is a relationship between X and Y in the population, right? People usually say we are interested in finding out whether there is a relationship between X and Y. That means we are really interested in finding whether there is a relationship between X and Y in the population or between the two variables, X and Y. So therefore, in that case, what we are interested in can be written statistically as a test of hypothesis. We want to test whether the population correlation coefficient, Pearson correlation coefficient, or whether the population Spearman correlation coefficient is zero or not. So can't we say that whether the population correlation coefficient would be zero or not by looking at the sample correlation coefficient? Not necessarily. Sometimes you might see a somewhat large sample correlation coefficient, somewhat large and different from zero sample correlation coefficient, but that sample may have come from a population where the population correlation coefficient is actually zero. That is possible, right? Even from a population where the population correlation coefficient is zero, when you get a sample, you might get a sample for which the sample correlation coefficient is somewhat large, like 0.5, 0.4, 0.6. That kind of values are possible, even though the population correlation coefficient is zero. So in other words, even though there is no relationship between X and Y in the population, sample may show that there is a correlation between the points in the sample, and therefore some people will wrongly conclude that there is a population, there is a relationship between X and Y in the population also by directly looking at the sample quantity only. That is the wrong thing to do. So therefore, that is why we usually carry out test of hypothesis to test whether what you see in the sample is enough for us to decide whether there is a relationship with the population or whether there is no relationship between X and Y in the population. Right. A non-zero sample correlation coefficient RORS does not necessarily imply that the population correlation coefficient is non-zero. So to see whether the sample correlation coefficient, what the sample correlation coefficient tells about the population correlation coefficient, we need to carry out a test of hypothesis concerning the population correlation coefficient. So that is where statistical inference comes. Right? So therefore, if you are interested in finding out whether there is a relationship between X and Y in the population, especially whether you are interested in testing whether there is a linear relationship between X and Y in the population, you would test H naught rho equal to 0. Here, rho is the population correlation coefficient, not the sample quantity. So you are testing whether the rho is equal to 0 versus the alternative maybe rho is not equal to 0, or whether rho is positive or rho is negative, right? Depending on what you really want to test, right? So this one is called the null hypothesis. The null hypothesis H naught rho equal to 0 state that there is no linear relation between the correlation, right? In the population between the two variables. Right? So that is commonly applied test, and whenever you calculate a correlation coefficient using a statistical package, usually the output of this test is given automatically. Even though we don't ask it, it gives you automatically. Right. So here, computer carries out some tests called it's also called a t-test. It's a type of a t-test. Using this formula, it calculates a quantity called t statistic. Notice here, it is calculated using R, the sample correlation coefficient. Right. So we are testing about the population correlation coefficient, but we are testing it based on a quantity calculated based on the sample correlation coefficient, yeah, using the sample correlation coefficient R. Right. So, how do you decide once you calculate this quantity? Well, there's some theory behind this. I cannot explain all this theory, but just to mention briefly, what you do is we look at this quantity that we get is large value or value close to 0, right? If this value close to 0, that is an indication that this hypothesis may be correct. It's more likely that this hypothesis is correct. If this quantity is a large negative or positive value, but in absolute value it is large, but it can be negative or positive, that is an indication that this hypothesis may not be correct, and therefore the alternative hypothesis is the more likely hypothesis to be correct. Correct. Right. So how do we decide whether it is small or large, this value? Well, that is decided based on some statistical theory. We can show that if H naught is true, if actually the population correlation coefficient is 0, then when you calculate this quantity, that quantity may be in a certain distribution, and people have shown that that is a t distribution, right? If xy follows a bivariate normal distribution, so there are some assumptions, right? Remember, when you are testing a hypothesis, always this test has been prepared by some person, and he has prepared this test to test whether the correlation coefficient between two variables is 0 in the population when x and y are jointly normal distribution, bivariate normal. Right. So if x and y follows a bivariate normal distribution and rho is equal to 0, then theoretically this quantity should have a t distribution with n minus 2 degrees of freedom. So what the computers are doing is actually using this theory, it is calculating something called the p-value for the test. P-value. I'm not going to try to explain that in this case. I think I remember I explained the meaning of the p-value in the workshop. So therefore, I'm not going to spend time on that now. The computer gives you, using this theorem, right, theory, it calculates the p-value and gives it to us. Right. So what people do is check whether the p-value is less than like 0.05, some value. Usually considered threshold value for the p-value is 0.05. So if the p-value is less than 0.05, people decide that H naught is wrong. Or they decide to reject H naught and then accept H1. On the other hand, if the p-value is larger than 0.05, then they say we don't have enough evidence to reject H naught, and therefore we decide that rho is equal to 0. That means there is no relationship between the x and y in the population. So that's how you make some conclusion about the population correlation coefficient based on the sample correlation coefficient. Right. So just because R is like R is different from 0, we cannot necessarily say rho is also not equal to 0. Right. Even if, for example, R is equal to 0.4, you might say that when you calculate the p-value may be uh, large, and therefore you do not reject S naught, and therefore you will finally decide that the population correlation coefficient between x and y is 0, and therefore in the population there is no linear relationship between x and y. Right. Of course, you will carry out this test only if based on the sample, at least there is some evidence of a linear relationship, but you don't know whether that apparent linear relationship is a strong enough relationship to decide whether population has a strong linear relationship or non-zero linear relationship. Non-zero linear relationship. Right. So if the joint distribution of x and y deviates substantially from the bivariate normal distribution, the p-value given by the computer may not have a real meaning, and in that case, making conclusions based on the p-value may lead to erroneous conclusions. Right. Or if you just look at the p-value without even looking at the graph, and you have calculated this correlation coefficient and done the test when there are outliers, again, the p-value given by the computer may not be valid. So if you directly calculate the p-value use the p-value coming from the computer without doing anything else, your conclusion may be questionable or invalid or completely wrong. Right. Right. So here I have an example. Suppose you have this situation. Right. So when you look at this you can look at this one. You will say in the sample there seems to be no relationship between x and y. Of course, when you calculate the correlation coefficient for the sample, you get 0.22. That also indicates that there is no relationship between x and y in the sample. So therefore, in that kind of situation, when the sample doesn't indicate association, then definitely in the population also there is no relationship. Not definitely, but most likely that in the population also there is no relationship. Right? Because this is a random sample came from the population. So therefore, but it's better to check. Sample says there is no correlation coefficient in the sample, but there might be, right? So therefore, it's better to check whether the rho is equal to 0, right? But remember that test is valid only if xy are jointly bivariate normal, right? So there are tests to check whether the xy points in your sample are bivariate normal. But most of the times people only look at whether x is normal separately and y is normal separately. That is not the most correct thing to do, but that is what many people do, at least. Right? If x and y are not normally distributed jointly, then of course x will not be normally distributed, y will not be normally distributed. So therefore, that is what many people do. But on the other hand, even if both x and y are normally distributed, that doesn't necessarily indicate that xy jointly bivariate normal. That is the problem. But many people ignore it, and usually, even in uh, highly recommended books, they only check the marginal distributions, whether the marginal distributions are normal or not. So that's why what I have done here, I have using something called Shapiro test. This is the R code for that. There's a test called Shapiro-Wilk test for normality. I have tested whether the X values are normally distributed. So this part is the output of that test, and this here the null hypothesis we are testing here is X values are normally distributed. That is H naught. H1 is X values are not normally distributed. So the p-value here is 0.99, that is almost 1, is definitely greater than 0.05. Therefore, we do not reject H naught. We do not reject H naught. That means we accept H naught. What is H naught? H naught is X is normally distributed. So therefore, when the p-value of the normality test is larger than 0.05, we decide that the data are normally distributed for X here. And similarly, I test whether the Y values are normally distributed using the same test. You can see the p-value is greater than 0.05. Therefore, we can decide that Y's are normally distributed. Right? But remember, as I mentioned, X and Y may be individually normally distributed, but still XY jointly may not be normally distributed. But people don't care that much about that. If you have enough sample, people usually carry out the test, right, for the correlation coefficient, right? So now, because X and Y are, just assuming that X and Y are jointly normal, we carry out the test for the correlation. We carry out this test using the T statistic and T test, right? So we are testing whether the rho is equal to 0. That is this test, correlation test between X and Y. And there it gives you the T value, that is the value of this test statistic. That is not important to us, right? But it gives you, and it gives you the degree of freedom of the T distribution. And this is the important thing, P value of that test. Right? So P value of this test is greater than 0.05. Therefore, we say we do not have enough evidence to reject H naught. Which H naught? This H naught in this case. So we do not have enough evidence to reject H naught. That means we accept this H naught, and therefore we conclude that in the population, Pearson correlation coefficient is 0, and therefore in the population there is no linear relationship between X and Y. So that is the conclusion. So let's look at another example. Suppose you have this kind of scatter plot. So this, for the sample, it seems there is a linear relationship, negative linear relationship. Actually, when you calculate correlation coefficient, it's a somewhat large value here, negative 0.607 you can approximately take. Right? So the correlation indicates that the sample correlation coefficient sample correlation coefficient is somewhat high here and but negative. So anyway, to test whether this sample correlation coefficient enough for us to decide that the population correlation coefficient is also non-zero, we have to carry out the test. Otherwise, even a sample correlation coefficient as large as this may come from a population where the population correlation coefficient is effectively 0. So therefore, in order to test that, we have to carry out the test of high pass. So as previously, I looked at whether the X values are normally distributed. Here, P value is 0.09. So still it's greater than 0.05. Therefore, I will decide that, okay, X is approximately normal. And similarly, for Y values, normality test gives you P value 0.43. So again, therefore, I can decide that the Y values are reasonably normally distributed. And therefore, I assume that X and Y are bivariate normal jointly. And therefore, we carry out the correlation test between X and Y. And then the p-value comes up as 0.000, so almost zero, right? So that means point is less than 0.05. So therefore, we have enough evidence to reject H naught in this case. What is H naught in this case? H naught is that we are testing whether rho is equal to zero. H naught is saying rho is equal to zero. So we reject H naught in this case means we decide that rho is not equal to zero. Okay, so that means first of all we can decide there is a linear relationship between X and Y, between X and Y in the population. There is a linear relationship because rho is not equal to zero. Then the question comes, what is that? Whether the relationship is a weak linear relationship or a moderate linear relationship or strong linear relationship. So for that, to get some idea about that, usually we calculate a confidence interval for the population correlation coefficient. Now we know that it is not zero, but what can be the value then in that case in the population, right? So computer gives us a confidence interval, this confidence interval. This is the 95% confidence interval for the population correlation coefficient rho. And it is between 0.93 and 0.62, right? So therefore, we can say that there is a negative linear relationship in the population. The strength of the correlation coefficient is between, that is the value of the rho is between negative 0.93 and negative 0.62. So therefore, we can say the existing relationship, linear relationship between X and Y in the population is somewhat moderate to strong. We cannot say exactly moderate to strong linear relationship. There is an evidence based on this particular sample, right? Based on this particular sample, there is an evidence that in the population, there is a strong to moderate linear relationship between X and Y. Right. Similarly, hypothesis test for Spearman's correlation coefficient. So you would carry out that kind of correlation test to test whether the population Spearman correlation coefficient is zero or not when there is a monotone nonlinear relationship, evidence of a monotone nonlinear relationship in the sample. So in that case, the R command that you use is the same as this command here. In this command, correlation test, when you say between X and Y, there are several options actually. You can choose the method, but the default method is it's using testing about the Pearson's correlation coefficient. So in this case, we wanted to test about the Pearson correlation coefficient. Therefore, I don't have to mention the method here. But here, because I want to now use the test about the Spearman, I have to specifically mention, right? So command is the same, X and Y, but now I have to use the method Spearman's correlation. So therefore, I have to mention it. Otherwise, if I don't mention this, it will still carry out the Pearson's correlation coefficient, which is not the correct one to do in this case. Right. So in this case, we don't need a normality test or anything, right? For this test, we can carry out as long as the data appears to be like this monotone and nonlinear, then this test is valid. So here the test has been carried out, the p-value is almost zero. Therefore, we can decide that in the population, there is a non-linear, monotone, positive relationship because our rho is the sample correlation coefficient is positive. And actually, in this case, it has not given us a confidence interval. It has just given you the sample correlation coefficient as an estimate for the population correlation coefficient, right? So it says sample estimates for the rho is 0.93. So that means that's what we in that case use as an estimate for the population Spearman correlation coefficient. So therefore, we can interpret the population relationship as a positive, strong, monotone, nonlinear relationship between X and Y. So now it's clear to you, before performing any hypothesis test for a correlation, a scatter plot should be always be examined to check the nature of the relationship and the presence of clusters, nonlinear patterns, or influential observations, outliers, and so on, extreme values. Right. So that I like to at that point, this point, end the first part of this video. That completes to a certain extent the correlation analysis between two variables, numerical variables, X and Y. Right? Correlation analysis between two numerical variables, X and Y. Right. So I'll stop this part here, and then in the second part, I will talk about regression analysis.